Okay, are we live?
Hi, you are live. So let's start.
All right. Thanks very much for the video introduction. We are Dylan Woods and myself is Hans-Jakob Wagner. And we're super delighted to present today a quick presentation on two projects that we did during the last years at the Institute for Computational Design and Construction at the University of Stuttgart. Under the topic of computational design and construction in performative timber architecture. So at the Institute of Computational Design, we're basically researching on three main topics within the architectural discipline. That is computational design, digital fabrication and construction, and biomimetics. And the first project that we're going to talk about is the Bugavoot Pavilion. It's a collaborative research effort that we finished in April 2019. So by now it's a bit more than 1 year old. It's a collaboration between the ICD, the ITKI under Professor Knippers, the Müller-Blaustein Timber Construction in Blaustein, and Bundesgartenschau Heilbronn is the national horticultural show here in Germany, and the robotics company BEC from Reutlingen. So the Buga Pavilion spans 30 meters across a central event space at the Bundesgartenschau in Heilbronn. And the main characteristic of this building is that it's a double curved timber shell. Now, shell structures have quite a history. Most of you will be probably familiar with Hans Isler and maybe more with Felix Candela and so forth, who built like very astounding and thin material effective and performative concrete shell structures. The thing though with these shell structures is that you basically need to build them twice because the formwork is so elaborate that you need to basically construct it with a lot of manual labor. And that's why we can't see really a lot of these shells anymore today. It's also interesting that we can find these kind of shell structures in nature. There is a peculiar sand dollar that has a skeleton out of that is made out of singular plates that are connected with finger joints. And this kind of principle is transferable into construction. And it's interesting because if you build a double curved shell structure out of planar segments, you can produce them out of a planar source material. And at the same time, you derive at a geometric pattern of the shell structure that somehow represents the three-dimensional form of the shell. In 2014, the ICD and the ITK already built a shell structure like this. This was the Landesgartenschau Pavilion in Schwäbisch Gmünd. Back then, the shell structure was built out of beech plywood with 50 millimeter thick plates. Now for the Bundesgartenschau Pavilion, the question was like how to bring this building system into a new performative realm. And if we compare the two buildings just in footprint, you can see that the Bundesgartenschau Pavilion is a dimensional jump. It's 3 times the span. It's 4 times the floor area. And the challenge that we set out to address is that we wanted to keep the material usage per square meter shell area the same. So already coming from a very thin shell of the Landesgartenschau Pavilion, we try to address the same topic or to keep the same material, even though we have like way more span. And how did we try to address this? So the section of the Landesgartenschau Pavilion is a singular plate. And for the Bundesgartenschau Pavilion, we basically split that plate in half and made a hollow cassette or a hollow box out of it. So we have a top plate and a bottom plate. And the bottom plate, as you can see here, has a hole in the middle so that you can actually access the connections between the segments. And all components are glued together so that each cassette is really like a structural building component that is very strongly bound together. Additionally to the cassette, we then have a waterproofing membrane. We have battens and a facade panel out of 3-ply large wood. So to sum up, the project tried to reach 3 times the performance, but it also, by introducing the cassette, introduced 8 times the complexity into the building system. And the question now is, how can you build such a building in 1 year from contract to opening? This is typically the moment where each contractor or each client would say, okay, that's just like not possible, and you didn't understand how architecture works, right? And you don't understand the economics of construction. But what we're trying to push here in the research is a completely new understanding of how the potentials of digital technologies can actually change these economic principles, where you can introduce more complexity by leveraging robotic fabrication and by leveraging a co-design methodology, where you say you generate your building system and you conceptualize your building system from the start with all parties involved and with all topics in mind. With that, we built a large computational model that included the structural modeling and included all the detailing of the pavilion. So that is 376 cassettes, around 2,000 beams, 700 plates, 17,000 custom milled finger joint and connectors. To construct that pavilion, we devised our own robotic timber construction platform. And this platform is able to address a comprehensive set of typical timber construction processes. One aspect of this platform is also that we built it in a transportable fashion. So it really is kind of like a small factory in a box. You just bring it to your construction company, and you can locally then unfold the robotic platform and produce with the local timber construction company. This is the simulation of the robotic fabrication. You can see that we're applying glue on the plate, then we're placing the beams onto the plate, and we fix them with the nails. In reality, the platform looks like this. This is in the unfolded state, and the effectors look like that. We have the pneumatic grippers, we have vacuum grippers with multiple sensors to check and control the process and the quality. So this is the handling effector, and we have a machining effector here with a nail gun, with a motor spindle, and with a glue application head. And then it's important to match the simulation with the actual fabrication workflow. And then you can really accurately produce all of these 376 bespoke hollow cassettes. So first you put the bottom plate, you then apply the glue. You grip the beam and you place the beam onto the plate. Then you fix the beam with beech nails, and you can release the beam, and it's held in place. After the cassette is closed, the cassette goes into the press, which you can see here. This is a time lapse of the production. The assembly of one cassette was around 5 minutes. And here it goes in the press. After that, the cassettes were machined on the same robotic construction platform with the motor spindle. And in this project, the production accuracy was of crucial importance. You can see here the close-up of the finger joints, and this is the joint in the shell. So producing these cassettes with high accuracy was of highest relevance, so that you then on the construction site can assemble the pavilion just like a three-dimensional puzzle. And we were all very happy when the pieces came into the pavilion very, very easily. This is the cassette going in. Yeah. And with this kind of system, you can then build a very performative timber shell without formwork and with minimal material. Now just some more pictures of the pavilion on the summer island. Very nice interior. There was a lot of events that were going on in there, and we got a lot of good feedback for this building system. Okay, with that, I'll wrap up the Bugavoot Pavilion, and now Dylan is going to take over with the Erbach Tower.
Great. So the second project that we want to share is called the Erbach Tower, and it's built using an innovative method of self-shaping to create high-performance curved CLT. So this project emerges from a collaboration with 3 to 4 different research institutes and also an industry partner. So the main players were ICD, or Structural Engineering Group from the University of Stuttgart ITKE, and the Wood Material Science groups from ETH Zurich and EMPA Dubendorf, along with the industry collaboration with Bloomer Lehmann in Switzerland. So the project starts from a sort of more research side, in this case, asking the question of how we can synthesize the performance of materials with the sort of accuracy and precision of robotic manufacturing. So typically when we think of robotic manufacturing, something like this is what we imagine, where we have large robots that work on engineered materials, and they take sort of heavy-handed processes to subtract from them, bend them, melt them, cut them in many different ways. And the downside of this is that it requires a lot of refinement of the material, but also that the processes become ultimately overly complex just to produce a certain types of geometry. So in contrast, what we propose here is a concept of what we call material programming, one in which the shape is generated through the physical programming of the material itself, in this case wood, And in a similar way in which the movement instructions in the robot can be sent to machines, the parameters of active materials can be designed and physically programmed to generate shape. So why do we want to generate shape? So similar to how Jakob explained shell structures earlier in the presentation, this is very simple, that curved thin structures can carry higher load in comparison to the amount of material compared to flat sheets. In architecture, these types of curved geometries are really well known throughout the industry and throughout the world, and designing them has become much easier and also assembling them easier. But production remains still a bottleneck. So to produce curved elements is complicated, and it also requires a lot more material and expertise. And as a result, larger sheet surfaces like CLT become very standardized and rectilinear, which works in some cases, but it fails to take advantage of the curvature that we can gain structurally and aesthetically. So at the same time, shockingly, the same exact wood materials that we use possess the natural ability to change shape at large scales with high force. So these can be used to actually generate shape. And this is typically seen as a problematic aspect in timber construction. I'm sure most people in the industry know about this. When wood is cut, it's wet. When it's dried out, it tends to warp or bow or twist or cork. And generally, the approach is to try as hard as possible to prevent this. And what we want to do is really simple. We want to use this or harness this aspect to actually generate a design curvature. And the way that we do that is by first creating sort of models of how the wood shrinks and swells with our partners that are specialists in wood material science. We then put these into what we call a bilayer structure, where one layer is oriented 90 degrees to the other, and one layer shrinks when it is dried, and this generates curvature. So the trick is how we can understand this computationally, and through that, with our partners, we build rheological models of how the wood behaves at a very high level so that we can better predict the movement in the curved parts. This is then translated into a finite element simulation, where basically we are then able to model with very high accuracy how the pieces of wood deform. So in order to do this, first we have to gather a lot of parameters about the material, and then we put the wood into a bilayer structure, and we model how it deforms. Then how we use this shaping in the manufacturing process is that we first shape many bilayer plates, and then once they are curved, we put these pre-curved plates together along with a locking layer in order to create a form-stable curved component. At the same time, we do testing to verify that this type of self-shaping manufacturing produces parts that are able to withstand similar amounts of load compared to regular CLT. And using this high curve CLT, the form of the tower is created from the intersection of 12 cylinders. The slight angular arrangement creates a seemingly double curved surface active structure, that is, that it uses the surface curvature to its advantage structurally, and it orients the layers within the CLT in the direction of bending. Because the cylinders are all curved the same, we can also create an efficient production method in which they can be cut from larger pieces. And in order to use this, then we also need to engineer the custom layups and understand how this is affected by the load, as well as tuning and defining parametrically the relationship between the connection screws and the angles along these curved seams. Production begins then really at the sort of heart of the material in the sawmill, with the selection of the proper board thickness that's needed for the self-shaping. This is the most important criteria of the process, where we need to sort by moisture content, something that's already read in the factory but is not usually taken into account with this much detail. After the boards are sorted, we can put them into these large-scale bilayers, as we explained before. And then the bilayers are placed into a standard kiln drying cycle. Inside the kiln, the self-shaping movement is autonomous and smooth, and also clean and coordinated. So this happens almost like magic as the boards are dried out. The really high benefit of this is that you can shape multiple parts at the same time, and by simply tuning the parameters within them, you can also produce different degrees of curvature. So this is what it looks like in the factory. On the left, the plates are wet in the moist state, and on the right, they're curved after coming out of the kiln. After shaping, the parts are measured and recorded, and the data is used to improve our simulations. And then the plates are arranged into a multi-layer structure like this, which then form the components of the tower. All that we need to do then is simply trim the edges of the components in order to put in the connection detailing, so we avoid a massive amount of surface milling. And then the finished curved components look like this. They're then assembled into groups of 3 in the factory, and a weatherproofing membrane and a facade is added that's made of larch wood with a special UV wood surface treatment, which keeps the treatment transparent while still maintaining the color of the wood. The groups of 3 are then transported to the site and were assembled with very minimal scaffolding by a team of only 4 workers in a single working day. This creates a primarily wood load-bearing structure, which needs only a single piece of 10mm thick steel at the top in order to form the interface to connect to the polycarbonate roof. The completed tower cantilevers from the ground over 14 meters, and despite this, the incredible thinness of the surface is exposed at the bottom, where they open like a curtain framing the surrounding landscape of Erbach and the Rems Valley. From the exterior, the concave curvature creates sharp lines and crisp shadows, distinguishing it as a landmark, while the convex curvature of the interior creates an entirely new spatial impression of timber architecture, with light from above washing the pillow-like surfaces. Already, the tower has become a local landmark and a destination for those traveling by foot and by bike, while at the same time maintaining its delicate relationship with the rural surroundings. But as a research project, we also continue to monitor the moisture within the wood and the overall geometry to ensure that deflections are not exceeded. And this has formed an ongoing project around the structure. Slowly, the surface treatment has caused the facade to lighten in color, which further makes it blend in, while the interior retains the soft and warm color of the spruce wood. The surfaces are friendly and materially tactile, while the oculus on the interior isolates the view of the sky. And I think the overall point that we want to make is that by understanding the materials that we work with better, we can more effectively and efficiently use them to create sustainable architecture.
Yep. So with that, the 2 projects are the presentation of the 2 projects conclude. Just a quick introduction of what we are currently working on and what we believe is important for the next years. The computational design methods that we are currently investigating are going to be applied to also to multi-story timber construction projects, and this is the next step that we're working on. With that, thank you so much for inviting us, and if there's any questions, please contact us, or maybe we have also the time now.
Hi, good afternoon. Thank you for the invitation. I am Mariela Reyes.
And I'm Michael Anna.
Yeah, we both together direct the MAD Lab, that is the Material Design Laboratory of the Universidad Autónoma of Chile. We are currently based in the CTTC in Temuco, that is the Center of Technological Transfer in Construction. And we are a new lab, and as a first challenge, we aim to introduce the new technology in the wood industry to students of construction and architecture. And we have here in the lab a variety of tools at our disposal, like CNC machines, including 3D printers, mill and robotic arms, and a robotic arm system, and high accuracy scanners from traditional carpentry tools and machines for fine furniture making. That is more or less our setup. Our focus lies in exploring how traditional crafts can find its place in modern age, and how the inherent understanding and celebration of materials can be recaptured through this combination of disciplines between basically the past, how we've been doing things, and how we are looking to the future. So our presentation, it will be, we call it digital carpentry, and you're probably wondering what digital carpentry means. And to be brief, by this we refer to the mix of modern digital tools with traditional technique and knowledge. So for that, I will be, and Mike is gonna take care of the rest of the presentation. So Mike, I'll pass over to you. Thank you very much.
Yeah, thank you, Mariela. Just a little background of myself. I studied architecture in the UK, and I did my master's in University College London, the Bartlett School of Architecture, where I stayed on as a research assistant following my studies, and then went to work for the Architectural Association as the robotics developer for Hook Park. And now we've come to found the Mad Lab in Chile here. What is digital carpentry? What do we mean by it? Like, as Mariela said, it's this idea of like man and machine working together. Like, how do we kind of recapture some of these ancient technologies, ancient trades and skills that we had in the past, and combine that with the technologies that we have available to us now? So what I'll do is I'll take you through a little, a whirlwind history of timber, and how that's kind of influenced what we're working with in the industry, and then a little kind of like brief explanation of like the robotic systems we have available that we have experience of working with, and how that's going how that can be applied to some kind of real life projects. So what we had in the past, not so long ago, everything was done by hand, and kind of hand labor was the main force in the timber industry, and everything was based on tacit knowledge developed by the hand using the senses. And as a result, all the thousands of bespoke tools were created that allowed us to customize each and every project, and each craftsman would have his own kind of customized set inside of that. And to kind of complement that knowledge, there was also this incredible knowledge of timber and how it could perform and what its properties were. And kind of as we see in this slide here, from it's kind of a traditional shipwright's a drawing of how they used to take the actual natural forms of the timber and use those to create the parts for the ship, understanding how the bifurcation and its inherent strength could be used for the keel, for example, on the boat. And kind of bringing those crafts together, this is an example of the Church of Transfiguration in Kiski Island in Russia. And it just shows how, with kind of timber to timber joints in the 18th century, we're already able to kind of build large scale buildings with incredible complexity. And then as the world changed, industrialization came about, we started to have this disassociation between timber and forests, and where the actual timber was produced, and then where the timber was sold and used in cities. So this process of standardization took place, where people needed to understand how timber could be graded and understood separately from where it was created. So and machines. So this kind of started to shape all these tools and processes, and this idea of standardization and economic standardization of timber in the industry. And alongside that, at the same time, these industrialized machines were introduced, where you could start to work faster and more precise with timber. And again, at the same time, everything was happening all in one go. People like Armand Emmy was coming up with the Emmy system, which kind of combines individual timber elements with steel supports to kind of create these combined timber performing beams. And Otto Hetzer is kind of the godfather of glulam, was coming up with his system of how we could make stronger engineered timber components. And that's all kind of fed into the engineered timber systems that we have today, where we can kind of create these huge buildings which can perform far stronger than the natural wood in some cases, and also allows us to kind of create these huge buildings. Some of them even standing today. An example is the Malmö station in Sweden, which is kind of this colossal glulam beam structure, which kind of really showcases what timber could do even hundreds of years ago, or 100 years ago rather. So what do we have now? We've taken these machines and we've augmented them. We've started to bring the digital age into them, and CNC computation has allowed us to kind of create more complex designs and also begin to discretize and kind of add data and understanding and engineering to how we work with this timber. So it's kind of one of the early examples of this was on the brine baths in Germany. It was kind of one of the first timber buildings to start working with CAD/CAM to create these kind of like free-form grid structures whilst understanding how the engineering is feeding into it. And now we kind of have these larger scale buildings that kind of take care of this, like the Cambridge Mosque, which was constructed by Bleu Lemon. So you kind of see we're now at this stage where we've taken timber architecture to another scale, another level, and we have this real strong understanding of this kind of like unit of what timber can be and what it's standardized as, and kind of how we've quantified the data to understand how that timber can perform. And then we also have this really strong heritage of craft and understanding of how timber actually grows and is kind of used when it's carved and shaped by the hand. And now we have like robotic systems. So the CNC and the machine has kind of developed to the extent that we're able to now guide and program our tools to work with increasing complexity. So kind of what's a robotic system? What do people mean when they say robotic systems? And kind of how is that applicable to us? So when we talk about a robotic system now, generally people are referring to the robotic arm, the industrial robotic arm. So it's made up of the arm itself, its brain, as it were, the control system, the tool which you choose to put on it, in this case, for say a spindle, the cabinet which controls that tool system and communicates with the brain of the robot itself. And with that, we can then start to switch between whatever tool we need, a bandsaw, a circular saw, a chainsaw, and in the same way a carpenter would reach in and grab whatever tool was relevant for the job from his toolbox, the robotic arm can do the same. And then we can augment that movement and begin to retain that precision whilst moving it on an actuated rail, or we can even start to begin in positioners such as turntables or lathes. So these arms now are capable of doing almost everything that we were able to do by hand. We can now move our tool and shape it and make it form to whatever we want to work with, in the same way that a carpenter used to be able to. So then we've got a tree in front of our robotic arm, in front of our system. How do we actually get that to understand and see what's there, and how do we actually take advantage of it? So with data generation and simulation, you can start to create your designs in CAD/CAM and simulate how a robotic arm can move and flow around it with proprietary software, which is widely available now. And then what we need to do is kind of to collect the data that we're going to work with. In this kind of example here, you can see how like active scanning was used to pick up the geometry of a chainsaw on the robot in order to get the position of the chainsaw in relation to the robot so that it could then be programmed for use. And then after we've kind of got all this data of what we have in front and we've got the data of what's on the robotic arm, we can execute our programs. We can send this robotic arm to go and cut these incredibly precise and kind of like curated components. And then following that, we can take this data, look at it, and we can bring it back into the system that we're using. So even if there's a mistake or if there's some kind of deviation from the original component form, as working with something like a bandsaw will often move and get pulled by the timber, and you won't necessarily, for a millimeter error, want to disregard a component completely. You may want to bring that back into what you're using and reuse it. So by visualizing and bringing this data back into what we're working with, we're able to take it on and understand those errors and make use of them. So how is this kind of this new technology, this idea of the carpenter and the kind of the digital world coming together actually kind of used to us? So what we'll do is take you through a couple of projects that show kind of this idea and this workflow. So the first one here is Wakeford Hall. So this was the skeleton frame, timber frame construction for a library building in Dorset in the UK. So this was constructed in about 4-month timescale, and the frame itself was manufactured, the components, in 2 months. So it was quite a fast and quick turnaround. So all of the system needed to be developed for this. So we started with a series of test pieces, and we decided that in order to kind of create this frame, cross-LAN was the best way to move forward. It allowed us to have the ability to engineer and understand how each of these frames would perform. It allowed us to work with a kind of a timber that was engineered and would perform as required when we were actually putting it under stress. And we combined this with the robotic arm in order to allow us to achieve the accuracy that would be required to actually engineer this structure, all of these different frames coming together to work correctly. So here you can kind of see the earlier ideas of how these frames could be constructed and the initial issues that we were kind of meeting when we were working with this robotic arm. And that allowed us to kind of come up with all this diagrammatic and discrete data that define the geometry. So we started to kind of create this idea of a feedback loop between what we wanted and what was achievable with the actual arm itself. So there was a limitation to what the tool can do, and there was the freedom of the design and the intent to keep this as close to kind of a true timber frame building as possible. So as that developed, there was kind of this manual verification and manual checking and kind of seeing, does this live up to what we can do by hand? And then that fed back into the design again. So we were able to take what we learned from the initial components and then define how we wanted our cross-LAN to be manufactured, how we needed it to perform for the engineering drawing, and what was actually possible to be created with the robotic arm. And then using kind of CAD/CAM tools, we were able to then generate how our frames would be actually work and how they would be designed in relation to that. And as a result, we were also then refining and changing our system. So our bandsaw went from kind of being able to cut on one face to being able to cut on both sides of the bandsaw. So we started to create these kind of custom tools that again allowed us to kind of actually achieve the original design intent as closely as possible while still making this thing entirely machinable by the robotic arm. So then how were we going to position this? And we started to look at some machine imaging and using cameras to kind of get the data for how to actually position these frames. And it was extremely difficult as our robotic arm was static. It wasn't really possible to, within the limits of what we had, move these little colossal frames that were like 3 meters in length in some cases. It wasn't possible to kind of move these into various positions and retain the accuracy that we needed. So we kind of fell back to this original idea of a carpenter marking faces. And kind of inspired by this, we came up with a system where we created a set of CNC machined templates, which we used to define the glulam positioning, but we also used these to transfer the distinct positions that we needed to reference where the frame would be for the robot, and also where any of the kind of the flitch plate connections and any shear joint connections could also be located by hand with these as well. So then we were looking into the actual machining. So we started to kind of get the machining underway, and we kind of found that although somewhat slow machining with the bandsaw and retaining accuracy, we were able to kind of get this a really beautiful finish as a result. So we were just not needing to sand and removed a large part of the handwork of kind of making these components look really nice and kind of crafted. And then at the same time, we kind of wanted to avoid a bottleneck. So instead of automating the process of cutting the holes with a drill, we allowed the robot to kind of get on with machining and cutting with the bandsaw. And at the same time, this team of students were working on drilling holes and setting the positions of the flitch plates based on the digital data that had been transferred to the original components. So by kind of working with hand and machine in collaboration, we were able to really speed up the process there. There wasn't just one robot arm working. The robot was working kind of in coordination with a larger scheme of work. So then we kind of came to assembly, which fortunately actually came together very well and very smoothly. We were able to kind of position all these frames together and bring them into site and kind of achieve these really tight joints that were required for the system to work. And we then verified all this data using those initial reference markers and LiDAR scanning to see kind of how close this was in general. And we found that the structure matched with 5 millimeters within a 6 millimeter span. So over the entire height of the building, there's about 5 millimeters of error. So between the assembly process, the steel work for the grounding and the actual positioning of the frame on the slab, we felt like that was quite a good level of accuracy for the size of the frames that we were working with in timber. And by taking this digital data in, we were then able to kind of continue to work with this digital model that we'd generated from the components, and that then allowed us to continue to work with cladding the building in a more conventional manner very quickly by just retaining and continuing to use that digital data for generating the outer cladding system. So now here you can kind of see the frame system sat within the shell that was manufactured afterwards. And now we kind of have this fully clad timber frame building. That kind of was a really nice exploration of how you can work between the advantages of a robotic arm and kind of traditional methods in order to create kind of, in my opinion, at least really beautiful timber buildings. So the second project's on a slightly smaller scale, is kind of called material domestication, and this kind of started with kind of a collaboration between me and Mariella, where we were really interested in the kind of the inherent properties of timber and its natural forms and how they could kind of be harnessed and worked with, but at the same time kind of being able to break out of the inherent form of the tree at the same time. So how can you take advantage of its inherent strengths, but also be able to kind of work with it as a designer and as a maker. So we started to kind of scan the kind of bifurcations and these kind of like reaction woods where the wood has formed and changed depending on the elements and the kind of the different things taking effect as it's growing, and kind of laminating this timber up so that we could re-glue it back together in kind of custom sort of glue lam parts. And kind of the initial explorations were kind of a little more on the crude side, but they allowed us to kind of understand where the limitations were, how the timber wanted to crack and wanted to move, and also how there was this kind of real strong limitation on design still. It was very planar or very, very small curvatures based on how the wood had grown itself. So we went back to the start and we began to kind of look for geometries that were as close to what we wanted in the forest around us. Go and scan these geometries in sight and then bring them out into like digital form and look into kind of traditional techniques that could work with this process. So we looked into how steam bending could be used in traditional carpentry. It was used to stabilize timber, not only to be able to form and shape the timber, but also to be able to stabilize it to reduce cracking and reduce defects in the wood as it goes on. So we kind of came up with this steaming process where we were soaking and bag steaming, working in collaboration with the Lyme Regis Boat Building School to kind of tap into their tacit knowledge that those guys have, in order to kind of make a prototype chair based on using a bifurcation, but changing its form to be what we needed for the kind of the ergonomic constraints of a chair. So this began again with digitizing, kind of taking and collecting the data of the tree and kind of bringing and simulating it into the robot, and kind of figuring out how we were going to get the robot to follow the natural grain. So we were kind of like studying the grain alignment, the longitudinal direction of the grain, to get the strongest possible laminations that we could and the most complete laminations that we could, which just wouldn't be possible to achieve by hand, to kind of get these kind of perfect thin laminations consistently with a handsaw would be pretty much impossible, I would dare to say. And then transferring that and kind of actually really bringing that into the robot with these kind of simulated feedback systems, laminating the timber up, following the actual grain here. You can kind of see in this image of the robot actually following the kind of the form of the tree and kind of giving us these laminations that we needed. And then we kind of took them away and we were kind of steaming them in bags, the laminations, and testing what the constraints and what the actual laminations could achieve before they would break or before they would start to perform outside of what we needed, or they started to kind of get defects or any problems with it. And then we were refining the way in which we could kind of work with that by hand to kind of clamp and react to the natural way the wood was working. And that kind of allowed us to achieve this kind of prototype chair. So you can kind of see how we've kind of not only worked with the shape of the wood, but we've gone and formed it and shaped it to what we wanted, and then also started to machine and kind of change the shape of those laminations as well. And then following this, we were able to take what we'd created again by hand, redigitize that, and bring it back in again as a digital model to continue to kind of augment and bring new parts into that. So outside of the kind of the form of the lamination, we wanted to make the chair more comfortable, more supportive. So we kind of had these almost prosthetic limbs that kind of came out and held the user's back and their posterior to make the chair kind of more comfortable as well. So it was this idea of retaining the functionality and the practicality of what we were trying to do at the same time. So that's kind of like a quick shot through all of those projects where we were kind of working with that idea. So I guess what's next? What can we do with this? How is it relevant? And I think it's a matter of, as we're progressing the construction industry, it's an extremely complex and very adaptive place. Like everything is constantly changing and moving on site, and it is very difficult to suddenly implement rigid automated systems very often, or it can be kind of expensive and time consuming. So our focus has really been on how can we work with traditional methods and start to kind of create as fluid a workflow moving between digital and real in order to kind of like make better buildings, better kind of components, and really harness that in between space between the two disciplines, as that's kind of, we need better buildings and better timber now, not when we've kind of perfected these systems. So that's kind of where we are at the moment of kind of really trying to develop that and further that technology here in Chile. So we're always open to collaboration and hope people contact us and kind of help with developing systems or work on some new projects in the future. So thank you for listening, and hope you enjoy the rest of the amazing program for today.
Hola a todos, mucho gusto. Mi nombre es Andrés Mitnick y soy el CEO de Strong by Form. Muchas gracias a Corma por la invitación a presentar. No sé si todos saben, nosotros ganamos el año pasado el Wood Startup Challenge y para nosotros es un placer poder mostrarles en qué estamos ahora. Voy a compartirles nuestra presentación. Bueno, como les decía, nosotros somos Strong by Form, somos un startup que está basado en Chile y en Alemania, somos todos los socios chilenos, y la idea hoy día es mostrarles nuestra tecnología disruptiva y también mostrar qué somos capaces de sacar desde Chile hacia el mundo, para que vean que aquí en Chile tenemos una tecnología muy interesante. Strong by Form es una compañía que genera soluciones sustentables. Nuestro interés es desarrollarnos con el ecosistema y no a partir del ecosistema, y para eso hemos desarrollado nuestra primera tecnología que se llama Woodflow, que es una tecnología que genera composites en base a madera, pero de alto performance, trabajando la madera de una forma en la que nadie más la está trabajando hoy. Para introducir esto, les voy a presentar nuestro video corporativo de 1 minuto y luego voy a continuar. Bueno, al parecer no se escuchó el audio del video, pero bueno, van a escuchar lo mismo durante la presentación. Woodflow es lo que nosotros llamamos una madera digital, y van a ver por qué. Pero fundamentalmente nuestro driver es la sustentabilidad. Nosotros lo que queremos es traer soluciones sustentables a un mundo donde no hay alternativas sustentables hoy día. Y la madera efectivamente está en la punta de lanza de las tecnologías sustentables. Vemos que hoy día se están construyendo edificios de mediana altura en madera, que la industria automotriz quiere avanzar hacia hacer cosas en madera. Sin embargo, ¿qué es lo que está ocurriendo? La industria empuja hacia la sustentabilidad. Sin embargo, los materiales estructurales que son intensivos en emisiones de carbono en su producción, tales como concreto, acero, fibra de carbono o aluminio, es difícil encontrar alternativas sustentables porque las alternativas sustentables no tienen el performance estructural que tienen estos elementos. Entonces, si bien hay alternativas con menor impacto ambiental, su performance estructural no permite que sean un real reemplazo a estos materiales que son muy contaminantes en su producción, pero entregan este alto performance estructural. Es por eso que nosotros vemos que hay una triada que tiene que ser resuelta. Una triada que tiene que ver con la performance estructural, la productividad a escala industrial y la sustentabilidad. A modo de ejemplo, la industria automotriz ya ha logrado reemplazar ciertos interiores con fibras naturales, porque esas fibras naturales cumplen dos características, que es que tienen la productividad de la escala industrial y al mismo tiempo son sustentables. Pero ¿qué es lo que pasa? La carrocería del auto sigue siendo de acero o de aluminio en algunos casos. ¿Por qué? Porque estas fibras naturales no tienen el performance estructural que se requiere. Y esa es la triada que vemos que hoy día no está resuelta para, de nuevo, componentes estructurales. ¿Qué hemos hecho nosotros? Nosotros pensamos que con Woodflow logramos resolver esa triada. Es decir, Woodflow es un material que es sustentable, toda vez que es en base a un biomaterial como la madera, tiene la capacidad de ser fabricado industrialmente y por otro lado tiene alta resistencia estructural. Tiene otras características, como pueden ver ahí en nuestro prototipo, somos capaces de hacer dobles curvaturas, somos capaces de hacer densidades variables y somos capaces de generar ángulos que con otras tecnologías de madera claramente no se puede. Ese prototipo que ven ahí tiene entre 4 y 5 milímetros de espesor solamente. Esto es lo que se llama un biomimicry. La madera es un material de alto performance estructural en la naturaleza. De hecho, en tensión tensil tiene mayor resistencia que el acero. Sin embargo, nosotros no lo pensamos así porque la madera es un material liviano. Pero ¿cómo se transforma la madera de un árbol natural en un material tan sofisticado? Fundamentalmente porque el árbol optimiza su forma, su densidad y la orientación de las fibras, todas para resistir los esfuerzos a los que está siendo sometido. El árbol hace esto de forma natural. ¿Nosotros descubrimos esto? La verdad es que no. Durante la historia, las capacidades de la madera natural como material estructural han sido utilizadas múltiples veces. En particular, en la construcción de barcos tenemos ejemplos muy interesantes donde vemos que los diseñadores y los constructores lo que hacían era que miraban los árboles y a partir de la forma que tenía el árbol iban definiendo qué piezas del barco iban a sacar. Esto es una técnica que tiene cientos de años y que se sigue utilizando hasta el día de hoy. ¿Qué es lo que están haciendo ahí los fabricantes de barcos o los constructores de barcos? Lo que están haciendo es ocupar la inteligencia de la madera natural que genera altísima resistencia en poco peso para fabricar sus embarcaciones. Sin embargo, ¿qué estamos haciendo con la madera en el siglo XXI? Hoy día en el siglo XXI tenemos otros desafíos. Tenemos el desafío de sacarle el mayor partido al recurso forestal. Y la forma que hemos encontrado para sacar el mayor partido al recurso forestal es crear la madera de ingeniería. Quiere decir que agarramos la madera y la transformamos en pequeños chips que después volvemos a juntar. Esto es muy productivo y permite utilizar muy bien los árboles. Sin embargo, lo que hace es que este proceso rompe toda esta inteligencia natural de la que yo estaba hablando antes. Todas las propiedades mecánicas que tiene la madera natural se pierden en este proceso. ¿Y qué logramos? Logramos madera de ingeniería, que son materiales que son bastante interesantes, son estables, son eficientes, pero sin embargo reproducen las técnicas de construcción tradicional a las que estamos acostumbrados. En ese sentido, nos podemos imaginar un mundo hecho a partir de madera, como este que es el campus de Google que quieren construir en Toronto. Y eso suena una muy buena idea, pero ¿qué es lo que pasa? Las tecnologías actuales consumen cantidades gigantescas de madera para poder construir las edificaciones hoy día. Esto no es malo por todos lados, efectivamente son un depósito de carbono. Sin embargo, si nosotros queremos llevar la construcción en madera a escala de arquitectura, realmente a una escala global y ser capaces de construir ciudades de madera, la verdad que esta tecnología no es sustentable. No podemos pasar todos los árboles a transformarse, todos los bosques a transformarse en entidades productivas. Necesitamos hacer un uso mucho más eficiente del recurso forestal. ¿Por qué pasa esto? Porque en general tratamos la madera como pueden ver ahí, como si fuera hormigón. En el fondo, en la masividad de la madera están sus capacidades mecánicas. Y lo que nosotros tratamos de hacer es de romper esa misma dinámica. Entonces, ¿cómo la tecnología digital nos puede ayudar a hacer la construcción en madera más sustentable y realmente escalable a escala global? Bueno, eso es GoodFlow. Y GoodFlow lo que es un proceso de fabricación digital donde nosotros tomamos los estreses a los que va a estar sometido un cierto componente, los pasamos por nuestro software de optimización que optimiza en las dimensiones de orientación de las fibras, hace una optimización topológica y además hace una optimización por densidad del componente. Y a partir de este software nosotros logramos una pieza completamente optimizada que entrega la máxima resistencia utilizando la mínima cantidad posible de material. Este software luego provee las instrucciones a un proceso de fabricación robótica, donde un actuador en el fondo dispone las fibras, de la forma en que el software ha definido. Este proceso luego se prensa y obtenemos un componente GoodFlow. Es decir, GoodFlow no es exactamente una materia prima, es un proceso de fabricación digital donde nosotros partimos desde las necesidades y terminamos entregando el componente optimizado. A modo de ejemplo, ¿qué pasa cuando un cliente quiere una unión rígida? Hoy día un cliente que quiere una unión rígida necesita una solución como esa, es decir, necesita combinar dos materiales. Necesita por un lado la madera con la que está trabajando y necesita estas pletinas metálicas y los tornillos o pernos que permitan juntar estas dos piezas. ¿Qué pasa con esto? Aquí estamos usando dos materiales con propiedades mecánicas diferentes. Eso genera mayor probabilidad de fracturas en la madera y esas fracturas pueden maximizar la probabilidad de falla. Además, estamos ocupando un material intensivo en emisiones de carbono, como es el metal, puede ser acero, puede ser fierro, puede ser tinto, pero todos ellos son intensivos en emisiones de carbono y además es pesado. La densidad del metal lo hace un elemento pesado. ¿Cómo lo resolvemos nosotros? Hoy día nosotros tenemos una tecnología que nos permite fundir en una sola pieza las uniones. A la derecha tenemos una juntura optimizada topológicamente con la tecnología de GoodFlow, donde, como pueden ver, ya no necesitamos dos materiales, utilizamos un solo material, lo que hace que tenga consistencia mecánica. Todas las piezas se comportan a los estreses de la misma manera. Eso minimiza el riesgo de generar quiebres, por lo tanto, minimiza el riesgo de falla. También, por supuesto, un material que tiene menores emisiones de carbono, al contrario, es solo capturador de carbono. Y por otro lado, la estética la terminación estética que logramos también es bastante superior a lo que se puede lograr hoy día. ¿Cómo se lleva esto a la realidad? Y cómo logramos tener un impacto realmente en el mundo físico, porque lo que esperamos con Woodflow es realmente ser capaces de cambiar cómo se ve el mundo físico hoy día. Nosotros lo que estamos viendo, la visión, es que en el fondo los diseñadores y los arquitectos están trabajando en sus BIM, están trabajando en su software de diseño en el computador y generan las distintas piezas, componentes, losas, lo que sea que estén armando. Y lo que va a tener Strong by Form es que va a tener un plugin en estos software de diseño, donde en el fondo cuando el diseñador apriete el plugin, el software de Strong by Form va a saltar a la nube, se va a procesar la pieza y rápidamente le vamos a poder devolver la pieza diseñada en Woodflow, además de sus características mecánicas, de una estimación de precio y todo lo que necesita saber para tomar la decisión si quiere o no quiere utilizar nuestra tecnología. Luego, nuestra tecnología, hacer una fabricación digital robótica, es una tecnología liviana. Esto es, en el fondo, un alimentador, un brazo robótico, un actuador, una mesa de deposición y una prensa. Eso puede estar en distintos lugares de la cadena, o sea, de un fabricante que hace muchas otras cosas. Nuestra idea es poder licenciar la tecnología para que se pueda fabricar en múltiples lugares. Por lo tanto, tú vas a poder pedir directamente a tu fabricante Woodflow más cercano el componente que tú quieres y acceder a él. ¿Qué es lo que entrega Woodflow? Woodflow entrega componentes que son sostenibles, componentes que son ultraligeros, que entregan alta performance estructural, pero también cosas que hoy día no se pueden lograr con madera, que tiene que ver con ser capaces de tener freeform, es decir, nosotros podemos hacer cualquier forma que se nos ocurra con la tecnología Woodflow, podemos tener espesores variables, como les decía antes, podemos funcionar distintas uniones en una sola pieza. Y además tenemos una arquitectura de fibra que maximiza la resistencia. ¿Lo hemos probado? Sí, lo hemos probado. Nosotros somos una startup en etapa temprana todavía, pero esto es un avance desde que ganamos el Startup Challenge el año pasado. Nuestro componente ya resistió 350 veces su peso. Ahí lo que tienen es este componente que les mostré al comienzo, que tiene entre 4 y 5 milímetros de espesor, pesa 854 gramos y ya resistió 300 kilos en una prueba no destructiva, con mínima deflexión. Los que trabajan en madera saben qué pasa si ponemos un terciado de 5 milímetros y le ponemos uno de esos sacos encima. Rápidamente se va a doblar tanto que en realidad se va a caer, quizás no se rompe, pero se va a caer porque no se va a poder seguir apoyando. Y en ese sentido, Woodflow es un material que entra dentro de la categoría de Lightweight Construction. ¿Por qué es relevante esto? Porque somos una tecnología que su input es renovable, por lo tanto es sustentable, genera muy bajas emisiones de carbono, consume muy poco material, es un material reciclable, lo podemos en el fondo picar y los componentes Woodflow se pueden picar y se pueden volver a hacer nuevos componentes Woodflow y es muy eficiente en el uso de los recursos. Ahora, esto es una tecnología. ¿Cómo transformamos esto en un negocio? Nosotros estamos empezando a focalizarnos fundamentalmente en el negocio de la construcción y hacia ahí van nuestros primeros productos, pero también hemos visto mucho interés en la industria de la movilidad y fundamentalmente en la automotriz. ¿Por qué es esto? Porque estas son industrias que consumen altos niveles de materiales estructurales, sin embargo los composites han penetrado muy poco. ¿Qué quiere decir esto? Estas industrias están usando materiales del siglo XIX, con suerte del siglo XX, y están listas para ser disrumpidas. Lo que pasa es que esta alternativa sustentable y estructural no estaba disponible, pero hoy día sí lo está. ¿Cómo lo vemos? Vemos que podemos hacer que la madera hoy día la utilicemos para hacer cosas que hoy día no podemos utilizar en madera. Tener un techo como el que está dibujado ahí, donde están apoyados en un solo punto, con dobles curvaturas, sin que esa madera se raje, hoy día sencillamente no es factible con la tecnología que existe. Hacer esas uniones en madera sin tener que ocupar partes metálicas tampoco existe. Por lo tanto, estamos haciendo elegible a la madera para penetrar espacios donde hoy día no puede penetrar porque la tecnología no permite que dé su resistencia. Por otro lado, también estamos tratando de combinar madera con materiales regulares. Como pueden ver ahí, eso es una losa colaborativa de Woodflow hormigón. Esta losa permite sacar el acero, que es el material más caro de la losa, y optimiza ambos materiales topológicamente, la madera y el hormigón. ¿Qué permite esto? Esto permite fabricar losas colaborativas Woodflow hormigón en un espacio industrial. Permite prefabricación de esto, evita que el cemento tenga que ser puesto in situ y nos llevamos todo esto a un ambiente controlado. Estas losas son lo suficientemente livianas para ser transportadas y moverlas desde un facility industrial hasta una obra. Esto es algo que estamos desarrollando en colaboración con una constructora alemana especializada en prefabricación en madera que se llama Müller-Blaustein. Y pensamos que es una solución para los pisos de las casas prefabricadas en madera particularmente interesante. Por otro lado, en la industria de la movilidad, lo que vemos es que especialmente los compradores de vehículos eléctricos urbanos, compactos y subcompactos, tienen un gran valor por la sustentabilidad. Y ahí es donde en el fondo Woodflow podría ser capaz de desarrollar un chasis, o sea, una carrocería de auto a partir de nuestro material que sea totalmente sustentable e incluso reciclable. Por supuesto que esto va a tomar un tiempo más largo, pero como van a ver más adelante, ya estamos conversando con algunas automotrices que están interesadas en avanzar en esta tecnología. Nosotros hoy día estamos viendo esas dos industrias. Sin embargo, Woodflow puede tener múltiples usos. Nosotros tenemos que partir por algo, pero los invitamos a ustedes también a contactarse con nosotros y a que nos digan para qué creen que sirve Woodflow y dónde ven que puede haber mercado y un negocio. Sabemos que pueden estar en los muebles, sabemos que podemos hacer estructuras marítimas, podríamos hacer yates, podríamos hacer miles de cosas. La idea es hacerlas todas, pero hoy día nuestro punto de partida es la construcción. ¿Qué ha pasado desde que el año pasado ganamos el Wood Startup Challenge? Bueno, la verdad que eso nos abrió muchas puertas, nos dio mucha visibilidad y entre otras cosas nos permitió estar en Alemania en el BMW Startup Garage, donde les presentamos a ellos y ellos se sentaron a hablar con nosotros justamente porque nos decían, miren, madera digital de la forma en la que están mostrando ustedes, la queremos, no la podemos encontrar, ustedes son un startup pequeño de un país que queda muy lejos, sin embargo queremos avanzar más con ustedes y esas conversaciones han ido avanzando de a poco. Las compañías que han mostrado interés en Woodflow son múltiples y son bastante grandes. Como les digo, BMW, Volvo, Audi, Skoda, las automotoras están buscando esto, no lo han podido encontrar. Por el lado de la industria forestal también, la industria de los químicos también y la industria de la construcción también. Por otro lado, para poder llevar nuestra visión a la realidad, todavía tenemos que hacer algunos desarrollos tecnológicos y para eso hemos encontrado apoyo en los centros de investigación más importantes del mundo. Fraunhofer de Alemania está dispuesto a colaborar con nosotros. También estamos trabajando con la Universidad de Rosenheim, con la Universidad de Stuttgart y también somos bastante cercanos a la Unidad de Desarrollo Tecnológico de la Universidad del Biobío. Un poco la invitación es a que empecemos a cambiar el mundo hoy día. Hoy día se puede empezar a cambiar el mundo. Woodflow va a hacer un cambio en el mundo físico como lo conocemos y con esta tecnología podríamos efectivamente fabricar edificios de gran altura con materiales sustentables, podríamos fabricar autos que sean sustentables y múltiples otras cosas. Los invito a conocer más de nuestra tecnología en www.strongbyform.com y por favor, si les interesa, pónganse en contacto con nosotros porque lo que queremos es ser capaces de escalar. Muchas gracias.
Muchas gracias, Andrés, por tu presentación. Así damos por finalizado este seminario.
Today, lightweight technologies are
video.
essential
Ok,
to reach longer distances and buildings to use less raw material. However, the production of lightweight structural materials, such as aluminum or glass fiber, are extremely intensive in CO2 emissions. In Strong by Form, we've been inspired by nature to bring a sustainable replacement to these materials. By emulating tree structural efficiency, we created Woodflow, a technology that combines the latest optimization tools with a novel additive manufacturing process to produce sustainable timber-based composite structures capable of matching the performance of aluminum or reinforced plastics. Woodflow is sustainable. Woodflow is lightweight and strong. Wood flow is free-form, so it can have variable thicknesses and fuse complex assemblies into single parts. It can be used for structures for mobility, construction, and applications where only the imagination is the limit. Bring your ideas and join us in building a sustainable future today with wood flow. Today, lightweight technologies are essential.